Today, I am going to talk to you about design concepts. Before proceeding further on chemical reaction equilibria and phase equilibria, I am going to take our special topic on design concepts. Now, we have normally designed reactors. We have got two types of design. One is called steady state design and dynamic design. Dynamic design, okay, or dynamic state. Now, there are two different types of design, and today both steady state and dynamic design are important for any design of reactors. Now, I'm not going to tell you about the in-depth of the reactor design. Now, we can really, if you have studied kinetics, we know V by F. F is a meter cube volume of the reactor, and F is a throughput, meter cube per minute or meter cube per hour, whatever it is. So this is a throughput, this is a volume of the reactor. Now two things you can design. Based for a particular flow rate, we can design the volume of the reactor, or for a particular reactor is available, we can design F. Both are possible. Now I am now designing a reactor for a particular flow rate. Okay, and I'm not going to go into in depth of the design, but I'm just going to tell you I have designed a reactor for a pharmaceutical company, and for that reactor I got a volume of 100 meter cube, the reactor size. It's a CSCR, continuous source reactor. I got volume of 100 meter cube. Now I can have a single reactor of volume 100 meter cube, or two small reactors 50-50 meter cube from here to here in series, or three small reactors or 33 and 1 by 3 meter cube. So both all are same, 100 meter cube, 100 meter cube. So I am doing it single, a double, a triple. Now this is steady state design. This is a steady state design. Now if you go to industry and say I am a designer reactor, first thing they will ask is what is the cost? What is the profit for me? So money is a very important factor in industry. Now if you design this reactor and we make a cost analysis, I'm not giving the actual values, but roughly, suppose this costs 100 rupees. This is two reactors in series, this will cost rupees 60 or 65, and this costs about 50. This reactor, one reactor costs 100 rupees. If you make two small reactors, it's about 65, and three reactors is 50. Why is this costly? Bigger reactor means labor is involved, folding, welding, everything. Therefore, this cost of this reactor is very high. This is cheaper, and this is cheapest. Now, based on this steady state design, what will you choose? You choose this because it is cheapest. Okay, so it's cheapest. Therefore, based on the steady state design, I'll choose three reactors in series of volume 33 1 meter cube. That's what you do. This is steady state design. Now, let's come to what's called as dynamic design. Dynamic design. Dynamic design. Now, in industry, we have got what's called as a capacity factor, CF factor. It's called capacity factor. Now, suppose we got a 8-hour shift 8 hours. Okay, 3 8-hour shifts we have, and suppose I want a product of composition, say 92% purity. I can have plus or minus 1, 92, 93 or 91. This is 8-hour shift. Okay, the 8-hour shift, this is the 8-hour shift. I want this is my desired composition, 92%. I give a tolerance of plus or minus 1. It can be 93 or 91. Okay. Now, if you see the recorders in the industry, it keeps on changing like this. If my composition is within this band of 91, and here you see everything is within this, then its capacity factor is 1. That means all the products are within the specified is 91, 93. So if it is like that, it's called capacity factor is 1. That means the product is very pure. Now in certain cases, what happens is, in this 8-hour shift, some product will go like this. Something going outside our band. So suppose for example, this 80% of the time it's inside the band and 20% of the time is outside the band, then it is called capacity factor is 0.8. 0.8 means 80% of the time this product is within our band, 20% outside. Capacity factor is 0.8. That means you've got some bad product here which has to be reprocessed or thrown away. Similarly, if you've got capacity factor 0.6, that means 60% of the time it is within the bandwidth, 40% outside. That means a lot of reprocessing cost or throwing away cost is there. Now, let's come back to our original reactor. 100 meter cube, 50-50, 50-50 and 33 into 3. Now, it so happens that if you calculate it, you make a product analysis here, here and here. Here the capacity factor is 0.98. I'm not telling the calculation part of it, I'm just telling the result. Here the capacity factor is 0.73 and here the capacity factor is 0.65 or something. I'm not doing exact value, roughly. That means here 95.8% of the time the product is pure. Reprocessing cost is very less. Whereas 73 is the capacity factor, 27% of the product you have to reprocess or reprocessing cost or throw away. Here 65% is within the 35% is waste, reprocessing cost. Now what to do? Here you have to spend on reprocessing. Here you don't have to reprocess. According to a steady state design, this is the costliest, this is the cheapest, you have chosen this. Now, we have got what's called as payback period. Payback period. That is, the industry makes any investment, they want to take back the money. How long it takes? Normally they take a payback of 2.5 years. That means if they invest 1 crore, they can get the capital back in 2.5 years. That means the payback period is 2.5 years. Okay? If you take 5 years, means payback is 5 years. So in this case, the payback period, I'm not telling you the actual calculation. Payback period is here is 2 years and 2.25 years. Here it is 3.2 years and this is 3.8 years. The payback period. 2 years and 3 months, 3 years and 3.2 years and this is 3.8 years. And that means what? The investment they get back in 2 years and 2.25 years. Here the investment they get back in 3 years and 2 months and here they get 3 years and 8 months. So based on the capacity factor, this is the best because you are getting back your money fast, whereas here you are getting back money very, very late. Therefore, industrial normal prefer this one. Therefore, based on the capacity factor, okay, I am choosing the 100 meter cube reactor. Though the steady state design says that you choose the 33 meter cube reactor, but based on the payback period, your reactor of 100 meter cube is chosen. Why is the temperature? What happens in the big reactor? Temperature fluctuation may not be much. For the 100 meter reactor, if it's a big size, a small disturbance may not affect it. Whereas the third reactor, very small disturbance in heat or something like temperature goes. And for normally most of the reactions in chemical engineering are exothermic in nature. Exothermic, that means, and from equilibrium composition was temperature. Okay, higher the temperature, lower the conversion. Higher the lower the conversion. Now, 5 degree change in temperature in the reactor can change the composition to between 10 and 20%, roughly. That means product is very bad quality. Therefore, in the big reactor, the capacity factor is 0.98. That means its temperature change will not be much because the big size capacity is there. Temperature change may not be that product will be. Therefore, based on the capacity factor and the payback period, we are choosing the 100 meter cube reactor. But whereas by steady state design, we had to choose the 33. But overall, when you find out the payback period, 100 meter cube is better. Therefore, industry will choose this 100 meter cube. Now, if you have got more designs, if you want these more details, you can refer to Duvin, book by Process Dynamics by Rubin. Okay, and take up. Okay, then tomorrow we'll proceed further and go in for phase equilibria and chemical reaction equilibria. Thank you.